Chapter 13 is all about hurricanes, and there's so much material in this chapter I had to divide it up into 3 PowerPoints, 13A, 13B, and 13C. So this is 13A. You got that dramatic cover photo from your textbook of high winds from Hurricane Katrina hitting a suburb of New Orleans on the 20th of August, 2005. So in this chapter, we're going to cover tropical weather, which is quite different from mid-latitude weather, the anatomy of a hurricane, how hurricanes form and dissipate, the naming of hurricanes and tropical storms, that's always interesting to students, winds, flooding, and storm surge, the kinds of damage you can get from hurricanes, notable hurricanes in history, and the difference between hurricane watches and warnings, and also other hurricane forecast products. And we'll talk about at the end of the chapter how hurricanes may develop in a warmer world, if in fact we are warming up. All right. Tropical weather, which is defined as weather between 23.5 degrees north latitude and 23.5 degrees south latitude, is quite different from mid-latitude weather. The sun angle is consistently high, so you have all that incoming solar radiation beating down on the ocean surface incessantly. There are no seasons in the tropics marked by temperature differences. It's always warm. There is, however, a wet period during high sun and a dry period during low sun. So when there's a low sun angle, and it's not too much lower than the high sun angle, there's a distinct dry season. When the sun is high in the sky, there's a distinct wet season. Now, in the tropics, most weather is not severe. You just have groups or clusters of thunderstorms, basically squalls of thunderstorms. Either some of them can be very strong, non-squall clusters and tropical squall clusters that march across the tropical oceans of the world from east to west. In the tropics, winds do in fact blow generally from the east to the west, which is different than in mid-latitudes when they blow from west to east. The differences in pressure are subtle in the tropics, so we don't use isobars to depict differences in pressure like we do in the mid-latitudes on weather maps. We use what are called streamlines, which depict wind flow. So you can see the heads of the arrows. These are vectors that point to the direction the wind is flowing toward. As these vectors converge, that typically is the axis on which thunderstorm development occurs, and this is then called either a tropical wave or an easterly wave because they move from east to west. Occasionally, an easterly wave will intensify and become what we call a hurricane adjacent to the Americas. So what is a hurricane? It's when you have an intense tropical cyclone, a cyclone of tropical origin, with sustained winds exceeding 74 miles an hour. That's 64 nautical miles per hour. We call them hurricanes when they're adjacent to North America. They form in either the tropical eastern North Pacific, our side of the U.S., or the tropical western North Atlantic, the East Coast and the Gulf of Mexico. Now, in other parts of the world, here's what they're called. Adjacent to Asia, the Pacific side of Asia, the western North Pacific, they're called typhoons. Near India, they're called cyclones. And near Australia, they're called tropical cyclones. The word hurricane derives from a language that was spoken a long time ago in some of the Caribbean islands called the Taino language in Central America by the indigenous people there. The word huracan in their language means God of evil. So you can see where that comes from. Typhoon comes from the Chinese word taifeng, which means big wind. That's self-explanatory. Later on in this chapter, we're going to explain to you how hurricanes are named adjacent to North America, how the National Hurricane Center in Miami goes about its business doing that. So let's look at hurricane structure now. In the center of the hurricane, there is this area with less cloudiness and light winds, where the air is actually sinking, not rising, and this is called the eye. Adjacent to the eye is an area called the eye wall, which is kind of a donut-shaped ring of the most intense thunderstorms that whirl around the storm center. And the tops of those thunderstorms can go 59,000 feet above sea level, which is just astounding. Spiral rain bands sweep toward the storm center as winds blow counterclockwise toward the center of the storm. Now that's in the northern hemisphere. In the southern hemisphere, the winds blow clockwise toward the storm center because things are the opposite in the southern hemisphere. The difference in atmospheric pressure can be as much as 60 millibars from the outer edge of the spiral bands to the eye. 60 millibar difference in pressure, a tremendous pressure gradient force, which is really something. This is a picture from the Space Shuttle Discovery of Hurricane Elena, which is quite dramatic. Adjacent to the eye the air rises and condenses into these huge cumulonimbus clouds, which make up the eye wall, that can produce as much as 10 inches of rain an hour. Now that's astounding. Just stop and think about that for a minute. In Fresno, in an average rainfall year, if we're lucky, we get 11.5 inches of rain a year. The eye wall of a hurricane can produce as much as 10 inches of rain per hour. So I think you can get the sense of contrast there. Now, near the top of the clouds, the top of the hurricane, the air is now relatively dry and it spreads out anticyclonically. And then it sinks and it causes clear skies on the outer edge of the storm. The release of latent heat near the eye wall causes higher pressures aloft. So right above the eye wall, you have higher pressure aloft, and what happens with that air sinks within the center or the eye of the storm, and that causes the eye's characteristic calmer winds and decrease in clouds. As the air descends in the center or eye of the storm, it heats up adiabatically, hence less cloud cover. Now, throughout the hurricane, temperatures actually remain fairly uniform due to the heat that's added from the warmer ocean surface. I'm going to show you some stepped art now, which gives you a structural look, a cross-section, if you will, of a hurricane. So you can see the inflow. It's associated with those outer bands that have the heavy showers. The eye is the place where the air sinks in the center, and then, of course, due to adiabatic heating, there's less clouds there. The strongest winds are associated with the first spiral outer band, which is the donut-shaped eye wall. Within the spiral band, you have rapidly rising air in this big heat engine we call a hurricane. And in between the spiral bands, you have areas with less cloudiness. This is where air is sinking, so clouds tend to dissipate a little bit. In the upper structure of the hurricane, you have air flowing out anticyclonically. Of course, this little cartoon shows you Florida in the distance, so you can tell you're in the Gulf of Mexico. So if you put everything together, here's the structure on the stepped art to give you a pretty good idea of the cross-sectional structure of a typical tropical cyclone adjacent to the Americas that we call a hurricane. Figure 13.4 shows Hurricane Katrina's eye wall and eye, as seen from the perspective of meteorologists in a Hurricane Hunter aircraft flying over the Gulf of Mexico on August 28, 2005. Sorry for the graphic being in the way, but figure 13.5 shows you a three-dimensional TRMM view of Hurricane Katrina on the same date. The TRMM is the Tropical Rainfall Measuring Mission. Special sensors on our satellites enable us to quantify how much rain is falling from the spiral bands of a hurricane. So we can look at rain rates per hour, and this gives weather service offices which are experiencing the hurricane's landfall some idea of how much rain to expect so they can issue appropriate flood warnings to people in harm's way. Now, hurricanes just don't form anywhere. They have to form in the right environment, and the right environment are the tropical waters of the world. Not in the mid-latitudes where water is cold, certainly not in the polar latitudes, but in the tropical waters where heat is constantly gained by that incessantly beating sun. And the water temperatures have to be at least 26.5 degrees Celsius or 80 degrees Fahrenheit for these tropical cyclones to even have a chance of forming. The activity in the western North Atlantic tends to peak in August, increase in August, peak in September, and then it tends to decrease in October and November when the sea surface temperatures get colder. This picture shows you tropical Atlantic sea surface temperatures in May 2002. It's color enhanced, so you can see the temperature differences there. Here is a historical look at Atlantic Basin tropical cyclones in the past 100 years, showing that there seems to be an increase in August, a peak right around September 10th or so, and then as the water gets colder, they do tend to decrease when you get into October and November. Tropical cyclones tend to form on either side of the equator between latitudes 5 and 20. They don't form right on the equator because there's no Coriolis on the equator. Coriolis effect helps the winds converge, so you need Coriolis for the formation of a tropical cyclone. They tend to form north of the equator because in the summertime, the intertropical convergence zone is north of the equator in northern hemispheric summer. And of course, they tend to form in southern hemispheric summer also when the intertropical convergence zone is south of the equator. That, of course, would be during our winter. Every once in a while, you can actually get a cold front that gets strong enough to move all the way down into the tropics. And those old frontal boundaries can also be a mechanism for convergence, where tropical cyclones can occasionally form. Not all tropical disturbances become hurricanes. Only a small fraction of them actually do. Studies suggest that major Atlantic hurricanes are more numerous when the western part of Africa is relatively wet, because what happens is clusters of thunderstorms from equatorial Africa or near equatorial Africa move westward out toward the eastern Atlantic Ocean and then go from land to water. Sinking air associated with the south end of subtropical high pressure systems can cause what we call trade wind inversions. That means warm air aloft. If there's warm air aloft due to a trade wind inversion above the surface, that tends to not be conducive for hurricane formation. Now in Chapter 14 we'll talk more about El Nino and La Nina and what that's all about. But suffice it to say for now that strong winds aloft, which cause strong upper level wind shear, are not conducive to hurricane formation, and those tend to occur in the North Atlantic when there's an El Nino episode in the North Pacific, which is the unusual warming of Pacific waters. The reverse can occur in the North Atlantic when a La Nina, or cooling of Pacific waters, occurs. So there is some sort of an association there based on research that there tends to be more hurricanes in the Atlantic when there's an El Nino in the Pacific, and vice versa. A storm develops as sensible heat and latent heat are transferred to the atmosphere from the ocean surface. Once again, I'm showing you this graphic of a tropical wave, figure 13.1, because I want to show you how thunderstorms organize somewhere along the intertropical convergence zone, or they could be associated with one of these tropical waves. A lot of heat energy, latent heat that you learned about in a previous chapter, is actually released during the formation of these clouds, during condensation. That warms up the air aloft, and that causes high pressure aloft to form in the upper troposphere. That causes the air aloft to flow away from the center, causing low pressure to form on the surface. So what you have is a tremendous amount of divergence aloft because of the formation of the clouds and the release of latent heat, causing high pressure to develop aloft, which then causes convergence to form on the surface. Remember, we learned in a previous chapter that if you have strong divergence aloft, that promotes strong convergence on the surface. The surface air now rushes to the center of low pressure, which continues to strengthen, and those winds increase in speed as they rush toward the center. This is the concept in physics known as the concept of the conservation of angular momentum. Whenever you see an ice skater on television, you see he or she is bringing their arms closer to their body and they spin faster. That's the conservation of angular momentum. The rate of heat transfer increases as the wind speed increases. That intensifies the storm. The original eye wall might actually fizzle out as the storm intensifies and a new eye wall forms. That's called eye wall replacement. This gives you a little cutaway of the structure of the storm with respect to surface air pressure. So where the pressure is lowest, that's the eye of the storm, the surface wind speeds are actually the lightest. The surface wind speeds are the strongest in the eye wall, as you can see by this graphic. Most hurricanes don't last for more than about a week, but if they remain over the warm tropical waters of the world, they can last much longer than a week. They weaken rapidly when they move over colder water. It snuffs off the energy source. Or if the layer of warm water in the ocean is shallow, not very deep. Of course, they dissipate rapidly when they make landfall. We can get all kinds of data about hurricanes from satellite imagery. That gives clues: visible infrared and enhanced infrared satellite imagery. Additionally, sensors on certain satellites, as I showed you in the TRMM graphic, can give a 3D dimension of the storm. And we have these hurricane hunter aircraft that can detect the properties of hurricanes, actually fly into the eye wall, which is quite exciting, as you might imagine. An instrument called the dropsonde, as you saw in the Hurricane Katrina video earlier in the semester, is released from the aircraft and gives us data every 5 seconds. And also a bathythermograph can measure the water temperatures under the eye of the hurricane to give us an idea of the latent heat energy being released. We get information from data buoys, and also when hurricanes get close to land, like Hurricane Andrew did in Miami in 1992, we can get data from ground-based radar as well. That ends Chapter 13A.